Welcome to an overview of direct piezo power, where mechanical stress is converted directly into electric charge. This slide introduces the basic idea. Applying force to certain crystals produces measurable charge, and the field sits at the intersection of material science, energy conversion, and emerging applications. The accompanying illustration highlights how stress flows through microstructure to electrical output and hints at future device possibilities. This slide breaks down the mechanism step by step, showing how applied mechanical stress shifts ion positions inside a non-centrosymmetric crystal, creating local dipole moments. Those dipoles align to produce macroscopic polarization and a measurable surface charge, which is proportional to the applied force. The diagram frames the process from crystal structure to dipole alignment and finally charge accumulation, so the chain from stress to signal is clear. Here we quantify the direct effect using the third-order piezoelectric tensor, which mathematically links mechanical stress to electric displacement. The slide also shows crystal class constraints. Out of 32 crystal classes, only about 20 exhibit non-zero piezo coefficients, while 12 do not, which dictates which materials are usable for piezo applications. This helps explain why material choice is critical for any design. This slide explains how poling maximizes piezoelectric performance. Ferroelectric ceramics start with random domain orientations, then applying heat and a strong external electric field mobilizes and rotates domains to align with the field. Once cooled, a remnant polarization is imprinted, dramatically boosting stress-to-charge conversion efficiency, and the illustration highlights how poling can push usable efficiency above 95%. The D33 coefficient measures charge density produced per unit compressive stress along the polar axis, so it directly drives voltage output. For example, a common PZT5H material has a D33 around 390 PC per Newton, while advanced single-crystal PMNPT can exceed 2000 PC per Newton, meaning significantly higher voltage for the same mechanical load and much better performance in charge generation applications. This slide focuses on two key performance metrics: the electromechanical coupling factor K and the mechanical quality factor QM. The coupling factor tells how efficiently mechanical energy converts to electrical energy, with high K improving sensitivity and bandwidth. The mechanical quality factor gauges damping. A high Q emitter produces sharp resonance and is valuable for narrowband sensors, while low Q emitters yields broader, more heavily damped responses. Comparing hard and soft PZTs highlights how doping tailors properties for applications. Hard PZTs use acceptor doping to reduce losses and raise QM, making them ideal for ultrasonic transducers where low loss matters. Soft PZTs use donor doping to increase the D33 coefficient and compliance, favoring low-force sensors and energy harvesters that need large charge generation under small deformation. This slide compares piezoelectric material classes and their trade-offs, contrasting relaxer ferroelectric single crystals with PVDF polymers. Relaxer crystals offer ultra-high coefficients and large actuation ideal for precision transducers and sonar, while PVDF and copolymers provide flexibility, conformability, and broadband response for wearable and curved surface sensors, highlighting the performance versus flexibility decisions designers must make. Underlying physics couples classical mechanical and electrical laws to predict piezo behavior. Hooke's law links stress to strain, and Gauss's law links electric displacement to field, and the coupled constitutive equations combine these into S equals S superscript E T plus dE, and D equals dt plus epsilon superscript Te. From these relations we derive charge output, resonant frequency, and impedance, guiding optimized material selection and device design. The electrical model represents a piezo element as a charge source, in parallel with a capacitance and leakage path, which maps directly to an equivalent circuit. Mechanical resonance is then matched electrically by adding inductance and a load resistor to enable impedance matching at resonance, a key step that maximizes power extraction and converts mechanical vibration into usable electrical energy efficiently. This application slide shows how the direct piezoelectric effect can be leveraged across domains. In consumer devices, it exploits impact-generated spikes for ignition. In infrastructure, PZT stacks embedded under asphalt harvest vehicle energy at scale. And in wireless sensors, MEMS cantilevers convert machine vibrations into microwatts, removing batteries, and enabling maintenance-free sensing in distributed systems. Finally, advanced materials and integrated systems promise greater charge density and system-level autonomy. Textured ceramics improve microstructure alignment, lead-free compositions address environmental concerns, and 2D layered ferroelectrics offer nanoscale enhancements. Coupling these materials with power harvesting circuits and management enables autonomous sensor networks and self-powered IoT, unlocking new remote monitoring and low-maintenance applications.